Aloha kako. Welcome to this month's edition of Live from NOIRLab. My name is Jamika Marshall, and I am an outreach assistant at the International, I'm so sorry. At the International Gemini Observatory. That was our timer making sure that we started on time, so it did its job. Yes, outreach assistant here at the International Gemini Observatory, which is a program of NSF's NOIRLab. I am very pleased today to tell you all about our guest. Before we get there, let me introduce our moderator. Our moderator is none other than my amazing colleague, Robert Sparks. And I'm just going to say a big mahalo nui loa to Rob. We've already had a few things we needed some assistance with, and Rob swooped in and made it happen. So thank you, Rob. All right, so Rob will be moderating for us. So if you are in our YouTube audience, please feel free to drop those comments and questions in the chat throughout the presentation, and our guest will answer throughout the show. And we'll also have answer questions at the end as well too, so no worries at all. Okay, so before we get to our guest, let me just do a quick introduction about the International Gemini Observatory and NOIRLab.
Today, the result of those efforts is the Gemini Observatory. Its twin
The video got a little bit ahead of me. Let me rewind that back. All right, so let me share my screen. So the International Gemini Observatory here is located in two places. We are the twins, and so we are located here, Gemini North, on the summit of Mauna Kea, which is where we are today here in Hawaii. We also have Gemini South, which is on central Chile's Cerro Patron. Now, the Gemini telescopes observe in visible and infrared light, which I'm sure our guests will talk about a little bit more later today. Now, Gemini's 8-meter, about 26.5 feet reflectors collect this light with mirrors that are coated with a special layer of protected silver rather than aluminum, which actually is the traditional coating for large telescopes. And we may be able to ask our guests to give us a little bit more insight on that as well. Now, one of the amazing things, one of the many amazing things about the Gemini Observatory is that we have these amazing large vents. And in the video there, you can see that the vents are actually open on the side. Now, those vents, which are open during observations, allows the cold night air to flow through the observatory. And this helps to produce more stable images. Now, having a telescope in the northern and southern hemisphere, and our guests will speak more about this, this allows Gemini to observe objects throughout the entire night sky in both hemispheres. In this video, I will drop it in the chat just in case you all would like to watch it on your own. All right, and so without further ado, our guest today, let me just highlight you. Stop my share. All right, so today's guest is none other than the Gemini's director, Dr. Jennifer Lotz. Jen Lotz, of course, the director of Gemini Observatory, which is a program of NSF's NOIRLab. She grew up in Florida and central Pennsylvania, and she's watching the NASA shuttle launches and the original Cosmos series with her dad. Now, after attending, this is Bryn Mawr College?
Bryn Mawr,
it's Bryn Mawr College, Bryn Mawr College, thank you. She earned her PhD in astrophysics from Johns Hopkins University in 2003. Now, Jen was a tenured astronomy at the Space Telescope Science Institute prior to joining Gemini in 2018. Excuse me. Now, her research specializes in galaxy evolution and morphology, the high redshift universe, and gravitational lensing, and uses both ground-based and space telescopes to track the growth of galaxies over cosmic time. And hopefully she'll be able to delve into some of that if you have questions on unpacking that. So first, let me give a big e-comma welcome to Jen. Thank you so much for being here with us today.
Thank you, Jamika. That was a fantastic welcome. I'm so pleased to be able to join you today, and I love that video, so I'm going to have to go download it.
No problem. Make sure that you have it. For those of you, obviously, you can't really see past our backgrounds, but I am happy to say that our director is actually here on Big Island with us today. Normally, she is at NOIRLab headquarters, which is in Tucson, Arizona. But yes, a special occasion for her to be here. So Jen, maybe you could start off by telling us why we have the honor of your presence on Big Island today, and actually for the past week. And once you finish that, feel free to start sharing your screen and begin your presentation.
Thanks, Jamika. Yeah, it's been a real pleasure to be back on the Big Island. We have had for the past week our semi-annual Gemini board meeting. And for the last 2 years, we've been having that on Zoom. And so this is the first time we've been able to meet in person. And I took great advantage of that. I got to go up and see the telescope and see those fantastic vents that Jamika was showing and show those off to our board members. Because I've been in Tucson, it's convenient for talking to folks in Chile and talking to folks in Hawaii. I'm in the middle of those time zones, but unfortunately it means that I haven't seen people in 3 dimensions for a long time. So that's been fantastic. And I'm just so glad I was able to actually do this as well while I'm here. So that's great.
And
Well, it is a pleasure, absolutely, to have you. And I apologize. I think Rob already has something from the YouTube audience.
yes, we already have something, and it was a question which I think is a fun question and may have been hinted at a little bit in your introduction. Maybe you could elaborate on a few of those things, because Liz Fleming from Memphis asks, what motivates you to excel at your amazing job? And so I think I picked up a few hints of things in your intro there that you might talk about based on that question.
Sure. Well, there's tons of things. I mean, I started as a kid watching Cosmos, Carl Sagan with my dad and just thinking that was amazing. And being able to go out and see the night sky, lying on in my backyard looking up was pretty awesome. And from there, having the opportunity to study astronomy in college and grad school, and just, what really gets me actually is the pretty pictures. So that's why I study galaxies and galaxy morphology, all the cool pictures. But now I get to be director. And so it's not just about the things that I'm excited about, but all the things, the many amazing ideas and science that's being done around the world, but also leading this amazing team of people at Gemini within NOIRLab. They're such a great group, and everybody's just motivated by helping everyone share the wonders of the universe. So that's a lot of fun.
Thank you so much for that, Jen. You may begin your presentation.
Okay, let me figure this out here. Okay, does that look good? Yep, I see Jamika nodding. All right, so Jamika did a fantastic job introducing Gemini. So this is actually Gemini North on Mauna Kea. And if you look, you can see Comet in the background there, which is pretty awesome. That was taken by one of our staff members at the time. Let's switch, there we go. So, as Jamika said, the observatory is actually 2 telescopes. We're 1 observatory, 2 telescopes. As the name Gemini suggests, they're twin telescopes, so 8 meters across, optimized for observing in visible and infrared wavelengths. And 1 is in Chile and 1 is in Hawaii. So Northern Hemisphere, Southern Hemisphere gives us great sky coverage. And we're also operated on behalf of the Gemini International Partnership. So that includes Argentina, Brazil, Canada, Korea, the United States. And then because we have a telescope in Chile is a participant. And because we have a telescope in Hawaii, the University of Hawaii is also a participant in this partnership. So what makes Gemini special? Many things, but one of our things that we're most proud of is the fact that we are very flexible and agile in our operations. And we operate a lot actually like space telescopes. We try to make the most of our time and adapt on a nightly basis to the evolving sky conditions so that we can best match the things that we're observing, the science programs, to what the conditions are on the sky. We also have adaptive optics at both telescopes to correct for distortions in the atmosphere. So being on the planet Earth, if you look up at the night sky, it's a little bit like looking up through a swimming pool. And you might notice that sometimes the stars twinkle and move a little bit more on some nights than other nights. So having adaptive optics means that we try to correct for the twinkling stars and the motion in the atmosphere to get the sharpest possible images with our amazing telescopes. And then finally, unlike some other telescopes, which I'll talk about in a little bit, we don't have a dedicated single instrument. We're not doing one big thing. We're doing many, many different things. So we have a really diverse set of scientific instruments that can answer a really diverse set of scientific questions. So we're all about discovery and exploration and helping our community of users try out lots of new ideas. So Gemini is extremely well poised for some of the most interesting scientific questions in astronomy coming in this decade. And we've made major contributions already, and we're going to build upon that legacy. So one, rapidly growing field of astronomy is the study of exoplanets, of the solar system, and now of exosolar systems. So here you can see a number of images based on science done at Gemini. Our knowledge of different types of exoplanets has just exploded in the last decade, and there are many different ways to detect and observe exoplanets, and Gemini is going to be doing all of them, from direct imaging to looking for things that are gravitational lens as a way of detecting exoplanets, looking at the wobble of stars to detect things through radial velocities, and to look for the dimming and brightening of stars as planets transit in front or behind them. So we're directly looking at exoplanets. We're also studying our own solar system. We've got amazing studies of Jupiter, and just I think today was a press release about the differences between Uranus and Neptune. And then, a new exciting field is the study of things that come from other solar systems. So here I have an artist's impression of the asteroid called Oumuamua. When astronomers first discovered this thing, they realized it had a really unusual orbit. And people believe that it actually came from a different solar system and is visiting our solar system. And Gemini played a leading role in trying to understand this object, and will play a leading role in understanding future objects.
Jen, if I may.
Yeah, go ahead.
Right?
Yeah, interrupt.
Yes, that's fine. Perfect. I was going to do our science update at the end, but you've already given us a little hint about the differences between Neptune and Uranus. We're going to have a sneak peek at that at the end.
Okay, good.
To that press release at the end, and maybe you can talk a little bit more about it after we play the clip at the end, Jen. We'd appreciate that.
Fantastic.
Thank you.
Okay. Another area of discovery that we expect to be really exciting in the next decade is the study of what we call compact objects. So that's really looking at very dense stars or black holes. And one of the exciting things about those objects is when they collide, they're a contributor to the recent detections of gravitational waves. Sometimes when they collide, they actually also produce an explosion that's visible. And so that, a growing field is what we call multi-messenger astronomy, not just using light, but using things like gravitational waves or high energy particles to further probe the universe. So that often requires the agility that I talked about before, being able to very rapidly move your telescope, point at different objects, try to figure out, we know a gravitational wave went off over there. Is there what we call an electromagnetic counterpart or visible counterpart? And so this image in the middle here is an example of Gemini's imaging of the electromagnetic counterpart, the visible counterpart to the gravitational wave that was discovered in 2017. And you can see circled in red is the fading of that kilonova. So that's going to be really exciting as not only more gravitational waves are discovered, but other such transient objects that might be discovered with the Reuben Observatory.
Oh, yes. I'm so glad, Jen, that you told us what was in those little red circles.
Yes.
Thank you. Multi-messenger astronomy may be a phrase that some of our viewers have seen or read or heard, but may not be super familiar with. So you alluded already to it, multi-messenger. We're getting information about the cosmos in different ways. Gravitational waves is one of the new messengers that we have, but one of the original messenger was just optical light, right?
Yes. And, for astronomers are maybe an unusual science in that all we can do is look at the sky, right, and observe. And so gravitational waves are really exciting because this gives us a new way of looking at the sky that we have not had open to us before. Okay. Let me move on. And so this last topic that I see as a real growth field is one very dear to my heart, the study of galaxies. And so I had to put a galaxy merger image in here that was taken with the Gemini telescope. This galaxies are essentially one of the fundamental building blocks of the universe. Stars and dark matter, our own planets, live in the galaxy called the Milky Way. And there are billions and billions of galaxies, and we can see those as we look further and further and further back in time. One of the interesting things that Gemini has studied and will continue to study is the connection between galaxies and what we call supermassive black holes that live in the centers of galaxies. So these are black holes that themselves are almost as massive as an individual galaxy. And just about every big galaxy we look at has a supermassive black hole in the middle of it. And you might say, how do you see a black hole, right? So this thing on the bottom here of the slide shows an artist's impression of something called a quasar. So black holes, and especially big black holes, will often accrete gas onto them, and that gas heats up. And so we can see the heated gas around a black hole, and we can see it from very, very far away. So, the study of black holes, especially these big black holes and their connections to galaxies, are one of the key questions that people are trying to understand in this field today.
I love that you have this artist impression here for us to see. Could you maybe give just a brief distinction between, tell us what a quasar is and how, what phase of the black hole we're seeing a quasar is?
Yeah. So a quasar is, when people came up with the name of quasar, they didn't know what it was. So I think it literally was quasi-star because it looked in an image of it. It looks like a very, very bright star often. Sometimes you'll see what looks like a bright star sitting in the middle of a galaxy. So it's really, what we've learned is that it's almost certainly a black hole. And, we have a big black hole sitting in the middle of our galaxy, which there have been amazing studies using Gemini and Keck and other telescopes around the world. And you can look and see individual stars going around that black hole. That black hole in our galaxy, fortunately, is not a quasar because we'd be in trouble if it was. But it might have been in the past. So, galaxies, often galaxies that have a fair amount of gas in them, the gas will settle in the middle, and it can start to orbit around that black hole. And as it orbits and falls into the black hole, it heats up. So they can be very energetic and emit a lot of energy out in jets. So you can see these two jets coming out of the disk here as described in the quasar. So that you got a teeny little black hole with a small event horizon in the middle, got a big disk of gas going around it. And then you can have these jets that are shooting out energetic particles and X-rays going out in either direction. And so even though a black hole in size is not that big compared to the galaxy it lives in, because of how much energy can be output by these quasars, it can have a big effect. Okay, I will continue on because I got a lot more slides. So the other thing that I think is really exciting is what the landscape in astronomy is going to look like in terms of new capabilities. So this is the James Webb Space Telescope as it was saying its farewell to Earth. I admit I woke up on Christmas morning to watch this launch, which is very exciting. And very soon we'll start to see science coming from Webb. I talked a bit already about LIGO, so that's the Laser Interferometer Gravitational Wave Observatory. We've had a couple sets of observations from LIGO already, but they keep improving it, they keep upgrading it, and so the next set of observations run is going to start in December of this year. And so we can expect that to be another exciting time when a lot of new gravitational waves are detected, and there'll be this scramble to try to figure out if there's a visible counterpart.
Can I ask a quick question here about LIGO?
Yeah, sure.
Could you tell us how does LIGO detect gravitational waves? And is there now an additional facility in Italy maybe that also is looking at gravitational waves?
Yeah. So I'm not going to be the best expert to explain this, but basically, they're looking for ripples in space and time. And so they have these very, very long antennae with very sensitive detectors that are measuring the separation between those antennae on very, very long baselines. And so there are several locations around the US and now around the world that can try to detect those ripples, those motions of those detectors. And as you can imagine, it is a technically extremely challenging measurement to make because, anything from small earthquakes to, just normal seismic noise can give you a signal. So by correlating those signals across the Earth, it can really help with that. And by having locations around the world, that helps us pinpoint where those signals are coming from.
Thank you so much. That was
that was a super high level and probably about the depth of my understanding. You should get a gravitational waves expert on to explain it in much better detail.
That's a good suggestion. We may do that, but no, thank you for that explanation so that we have a better idea of how that works. And here we have Rob. Rob, are you back?
Yeah, Rob.
You make me think of LIGO because back around 2003 or 4, I applied for an education job with LIGO and didn't get it. So I ended up at NOIRLab instead. So, but yeah, LIGO is a fantastic experiment. So I love seeing what they do. But we have several questions in the chat here now. First of all, we have a question: what role does dark matter play in the large-scale structure of the universe?
Oh, it's really, really important. So back when I was a graduate student, people were trying to understand the nature of dark matter. And that was really important for understanding cosmology because, at the time they were talking about two flavors, cold dark matter and hot dark matter. And, the kind of dark matter really affects kind of how the universe evolves and what we see over cosmic time. So we now understand that what we have is cold dark matter. And so these are, low mass particles. And what that means is that when the universe first formed, you first started forming the beginnings of galaxies, you started with very small density perturbations. So you start with little baby galaxies, right? And over time, those galaxies grow through galaxy mergers, which is part of why I used to study galaxy mergers. And that's really set sort of fundamentally by the properties of dark matter, and help us understand when we see what the cosmic microwave background looks like, what the properties are of galaxies over cosmic time. The opposite thing, a hot dark matter, you would have started with really big structures, right? You started something with big that would fragment down to something small. And we've clearly ruled that out. That's not that's not how the universe works. So I'm glad to say we've learned something about dark matter. But there, we still don't really understand what that dark matter particle is. And please don't ask me questions about that. But that's an element of intersection between physics and astronomy, where some experiments in astronomy can help put some boundaries on it, while particle physics can help put boundaries in the other direction.
Okay, thank you, Jen. We have a couple more questions here. How do ground-based telescopes like Gemini support space-based telescopes like JWST?
Yeah. So there are a lot of exciting synergies between Webb and Gemini. So I said Gemini, observes in the infrared. Well, Webb is all infrared all the time, and it observes, there's an overlap with Gemini's wavelength capabilities, but Webb goes even further to the red than what is possible from the ground with Gemini, or what is really difficult from the ground with Gemini. So Gemini scientists using Gemini have already, used Gemini to explore some ideas, identified some targets that are going to be observed in the very first cycle with James Webb. So, those quasars that I talked about, they'll be following those up in more detail with Webb. Some of the exoplanet studies we've done, they'll be looking at them at different wavelengths with different instruments to get different kinds of information that we weren't able to get with just Gemini alone. But I think it works the other way too. So sometimes you might discover something, certainly with Hubble, people have discovered new galaxies, new stars, new things. And there's only so many instruments, so many capabilities. And once you send a telescope out into space, that's it, right? Unless you send an astronaut to go get new instruments or cameras on it, which has happened with Hubble, but we're not going to do that with Webb, right? So there are some things that Webb can't do that Gemini can do. We can look at things in higher spectral resolution. Another thing that Gemini can do that will be hard for Webb is our agility. So Webb is big, it's expensive, and it's not going to move on a dime. So Gemini could, if there's an exploding star, Gemini could look at that within a matter of hours, where that would be really hard for James Webb to do. So you could imagine, a partnership there of how those two telescopes will work together.
That sounds like a beautiful synergy. I love that you use that word. Yeah, that's an amazing way to be able to support that the space-based and the ground-based can actually support each other's research, and not just one way. That is an amazing insight to have, and I'm really glad you elaborated on that. And if we could stay with James Webb JWST just for a moment. You did say, once the telescope is out in space, that's where it's going to be. So unlike Hubble, which we could go up and make repairs to, we're not going to be able to do that with JWST because it's in this L2 Lagrange 2 spot. Could you maybe tell us about Lagrange spots and why it's put there?
Sure. So Lagrange spots are basically resonance points in the solar system, and this is a place where it's possible to put a telescope at this point at a stable resonance point within the Earth, Sun, Moon system, and it will pretty much stay at what we call trailing Earth orbit. So it's going to move through the solar system with the Earth. It's not orbiting the Earth, but it's going to move, stay at about the same distance with the Earth as it goes around the sun, which is really nice. And it's a good thing that it's far away from Earth, because that helps it with the infrared sensitivity. It helps it doesn't, Hubble orbited the Earth every hour and a half. So there was 45 minutes when you really couldn't do much with Hubble out of every hour and a half, because it would be in the wrong place in the orbit around the Earth.
Oh, no, that's perfect. Thank you for explaining. Because, people who may not be familiar with that may just have heard L1, L2. And I was up early also, as you alluded to, on JWST launch that morning. And, they did a bit of explanation about Lagrange and how they came up with these Lagrange points. And we also use those Lagrange points, like those are actually around for all the planets, all the way out to where we see with the shepherding of the moons. Like in Saturn's shepherds, those are also in Lagrange points as well, right?
Yes. Yeah.
Wow. I love it. Thank you for those insights. Rob, amazing. Thank you for the comments and questions, everyone from the YouTube audience.
We got one more here. One more is in the queue. So one more from Liz. And this sort of dovetails nicely with what your headline of your current slide is here too, coincidentally. What role do you see Gemini having in future observations and discoveries?
All right, so I will get to that if we can be patient. So let me go on here. I think I'm only on slide 4 or something, so we're going to be in trouble, but that's all right. So not only will Gemini synergize with James Webb and LIGO, but we're very excited about the start of Reuben Observatory operations. So Reuben is also an 8-meter telescope. It's actually just across the way from Gemini South. I'm sitting on the same mountaintop, but it's a really different plan for Reuben. So Reuben has got a big camera. It's going to take pictures of the sky. It's basically going to cover the whole sky every 3 days. And so that's going to be a tremendous amount of data. And it's going to build up these really deep images of the nighttime sky. But you're also going to be able to look for new things that appear on the sky. So exploding supernova, or a comet, or an asteroid that's zooming through the solar system. And so Gemini is planning to play a really key role in the follow-up of new discoveries and science ideas that come out of the LSST survey, so the large survey of space and time. And then finally, further on the horizon, there will be even bigger telescopes coming to the ground. And so NOIRLab is actively involved with planning for the US extremely large telescopes. So those include the 30-meter telescope, TMT, and the Giant Magellan Telescope. So those are hoping to come online around the end of the decade. And of course, Europe is also building its own extremely large telescope, which looks like it will be showing up a little bit sooner, a few years before these. So let me move on and talk about what Gemini is going to do. So I talked about Gemini's strengths here, and the thing I wanted to highlight today was the new instruments and capabilities that Gemini is going to have coming online in just the next 2 to 3 years. There's really a lot, and they're going to be really exciting new capabilities that are going to be on this bigger landscape of a lot of new discoveries, a lot of new ideas. And so as I talked about the synergies, these new instruments are really going to help make the most of the next 5 to 10 years of astronomy discovery. So this is a complicated slide, but I just want you to take from this the big number of instruments, scientific instruments that Gemini has, and new instruments that we have coming. So they come in 2 flavors. One is what we call imagers, and these are basically cameras that take pictures, and they have different fields of view, and they cover different wavelength ranges. Some of them work with our adaptive optics systems. Some of them just use what we call natural seeing, so no adaptive optics. And then the other flavor of instrument is what we call spectrograph. We get spectroscopy. And that's usually looking at, a small number, 1 or 2 galaxies or stars or nebula. And we take the light from that, say, star, and we spread it out, like running it through a prism. And we can look in greater detail at some of the signatures of light that come from different elements, different molecules, that tells us about chemical composition. We can also look to see how that light is shifted, and that tells us about the distance to that object. It tells us about the internal kinematics of that object. There's just a wealth of information that can be determined from these spectrographs. And so coming online in the next few years are actually a lot of spectroscopic capabilities to Gemini. And I'm going to try to get to these in today's talk. So we've got something called Jwst. We've got an upgrade to one of our key spectrographs, Genius. We've got a new instrument that's a clone of an existing instrument called Lagrange 2. We've got an instrument that's both an imager and a spectrograph. It's called Scorpio. And then we have a really cool AO system designed to study exoplanets called the Gemini Planet Imager, and that is getting an upgrade as well. So let me talk first about Jwst, because that's being assembled as we speak. So Jwst stands for the Gemini High Resolution Optical Spectrograph. And this is designed to be the best in class of these kinds of objects. And this graph I have here shows Jwst, which is the top line, and its sensitivity as a function of wavelength compared to the other spectrographs available currently. So you can see it's above the rest of those lines. So that means that we'll get more light for less time and be more sensitive. There are a lot of interesting science cases to be done. The study of old and metal poor stars in our Milky Way, which tells us about how our galaxy came together. You can use this spectrograph to study exoplanet systems, look at their atmospheres. And a big survey that's planned, I'll say a little bit about, is to look at the stars in a really special kind of galaxy called the ultra-faint galaxies. And so we're planning to have this spectrograph ready for science by the end of June. Now, Jwst has had sort of a set of bad luck. So this is a plot, you've probably seen this, of COVID, and you can see that what the COVID over the last 2 years has case counts has looked like in Hawaii, Chile, and Tucson. So Jwst was put together by a consortium of folks from Canada and Australia working with the Gemini team. And, in February of 2020, the folks in Canada packed most of Jwst up and put it on a shipping container and put it on a slow boat to Chile. Well, February 2020 is maybe not the best time to put for this instrument to be headed off to Chile. And so we received it, a few months later. And unfortunately, we couldn't do much with it because the Gemini South Telescope was shut down for a while. So it sat in shipping containers, first on our facilities in La Serena. And then eventually we were able to move these containers up to the telescope where they've been sitting and waiting for quite a while. And what we were waiting for was to be able to bring into Chile those critical team members from Canada and from Australia and from the Gemini North team in Hawaii so that they could put this back together and put it on the telescope. So hooray, in April, just a month and a half ago, we were able to start bringing the team into Chile and start putting the pieces together. And so here you can see the team unpacking that crate. You can see them putting together the enclosure that surrounds this spectrograph. You can see them testing all the pieces and putting them together. And then here you can see light going through the spectrograph in that kind of rainbow mode that you would expect. And so fortunately, it did really well sitting in boxes for 2 years and, putting the pieces together, starting to put it onto the spectrograph, onto the telescope. And so in June was going to be able to test it with the telescope and actually start getting real astronomical light going through the telescope. So that's really exciting. We have a bit of a preview of some of the science that we'll get out of Jwst from studies that have been done actually with Gemini North with an instrument called GRACES. And so this was a recent press release that came out in January where a team from Canada started studying with GRACES, looking at the chemical contents in a very special set of stars. So this is a set of stars discovered by a space telescope, Gaia, which we believe is a stellar stream. So you see these traces of, collections of stars that look pretty unusual in the Milky Way. And we think that these are objects that have fallen into the Milky Way and are essentially the building blocks of stars. So that person who asked a question about dark matter, I said, you start with little galaxies and you grow them through merger. So this is this process in action. And the, metal poor stars are one way to see that. And so this particular stream, GRACES was able to determine that it was the most metal poor set of stars known in the Milky Way, if we think of it as originally a star cluster. And so you can see it compared to the other known star clusters of the Milky Way. So the Jwst team is planning to use this capability to study ultra faint dwarf galaxies. So this is a special class of dwarf galaxy that which we think might be the remnants of very old, the very first galaxies. And so studying the chemical content in those stars are going to tell us about the chemistry of the early universe. So I'm going to move on to another instrument that we're looking to upgrade. So the Gemini Near-Infrared Spectrograph is another spectrograph. It's here at Gemini North. It covers a wider range, well, actually a redder range than Jwst will. So it goes all the way up to 5 microns, which is really, really red. As not as high spectral resolution as Jwst, but it can be used with our adaptive optics system. And we've got two new ways of doing spectroscopy with G-nears coming through something called an integral field unit. And I'll say a little bit more about what that is. So the science with G-nears, because it sees so far into the red, it's really good at looking at very high redshift, very distant objects. And so it's been a real trailblazer in detecting these really unusual, very high, very distant, first supermassive black holes that are accreting. So I talked about quasars. So this is a detection of one of the second most distant known quasar. It's found to have a very massive black hole sitting in the middle of it, very massive for that time. That's equivalent to 1.5 billion times the mass of our sun. And because it was so special, we asked if we could have a special name for this. So here in Hawaii, there's a really great program working with local Hawaiian teachers and educators for unique discoveries on Mauna Kea to come up with Hawaiian names. And so the name that was come up for this object was Punuenea, and that means unseen spinning source of creation surrounded by brilliance, which is a fantastic name. I wish we could name all things that instead of J1007 plus 2115. But that's a lot of work. So the study of these quasars and other objects is one of the things that the new upgraded G-nears will do. So what this does is instead of just getting sort of one piece of a galaxy, it actually can get this kind of data, this kind of spectra for a bigger region of the galaxy. So this image is a little hard to interpret. So let me do this for you. This is an image of Centaurus A, which is a nearby galaxy. The orange box is zoomed in the corner there. And if you zoom in even further to just the very central regions of that's the field of view that this new integral field unit can do. And what it's going to do is instead of just getting one spectra, one slice of it, it's going to get many spectra over that smaller box you see in the bottom. So that's going to give us, multiplex the information that we find out about say, in this case, the center of galaxies, and be really, really great. And this, James Webb has similar instruments. This can be used in concert with James Webb. There's some overlapping science that can be done, and there's also complementary science that can only be done with this new upgraded instrument. So let me move on to the next thing that's coming. So this is IGRINS and its successor, IGRINS 2. This is also an infrared spectrograph. It's a little bit more like Jwst in that it's designed to be very high resolution, see very fine detail in this light that's spread out, and it gets a lot of information all at once. So what you see here in the orange is the light all the way from 1.4 microns to 2.5 microns. And if you zoomed in, you would see lots of little features identified. And those are features, molecular lines, many molecular lines that can be detected at this wavelength range. So we already have an instrument that was built by the University of Texas and by CASI, the Korean Astronomy and Space Science Institute. It's sitting down at Gemini South. It's a very popular instrument. And Korea is our newest international partner. And when they joined Gemini, they said, well, we'd really like to build you a new and improved version of IGRINS as part of joining the partnership. And so they're actively building it. They've made a few improvements. And this instrument will be coming to Gemini North at the end of 2023. And so there's an amazing amount of science that can be done with this kind of data, the study of exoplanet atmospheres, looking at ices on moons in our solar system, studying the molecules and star-forming regions, which tells you about how star formation proceeds, looking for new elements in other nebula, planetary nebula, and studying what's called young stellar objects. So these are forming stars. And so there was a press release a few years ago, which was a study with the existing IGRIN system where they looked at Triton, which is a moon of Saturn, and they are studying the ices on Triton, and they saw something that had only ever been seen in a laboratory before. So this just shows the power of having this very precise measurements and being able to, look for things that we haven't seen before. The study of these ices, I think is tied to the weather conditions on Triton, which is a really interesting way to study what other worlds are looking like. So let me talk a little bit about the Gemini Planet Imager 2. So this is a movie from the Gemini Planet Imager. This is what we call an extreme adaptive optics coronagraph. So coronagraph is something where you take the image of a bright star and you block it out. So if you see there's kind of a black hole in the middle of this image, there's a star there, and we don't want the light from the star, we want to see the light from the things around the star. And in this case, a planetary system. And in order to see those very faint planets, we have to block out the light of the star and have what we call a high contrast ratio, the ratio between the light of a star and the light of the planet. So the Gemini Planet Imager was a really successful instrument, and I'll talk a little bit about some of the things that it discovered. But the team that built it really thought they could do more. And so they went out and they got additional funding from the Heising-Simons Institute, from the National Sciences Foundation, and from the National Research Council of Canada to build a new improved Gemini Planet Imager, which was GPI 2.0. And so we've just shipped this out to the team, and I'll show you the pictures of it. And they're going to do these upgrades, and it's going to come back to Gemini North in 2024. So one of the things that team did was do a survey of, over 300, I think 300 and almost 400 stars in the nearby galaxy. And they're just looking to see if they can detect new exoplanets, direct images of exoplanets, or other companions, including brown dwarfs, which are essentially low mass stars, so low mass stellar companions. And this diagram shows, I'll try to unpack this for you. The dashed lines and the y-axis shows the mass of the companions that are found in Jupiter masses. And the things that are very massive, more than 10 Jupiter masses, are considered brown dwarfs. They've crossed that threshold into being a star. And the things below that threshold are considered planets. And then they looked at stars, the host star, that were lower mass, so less than 1.5 times the mass of our sun, and high mass, more than 1.5 times the mass of the sun. And they saw some very different patterns. And so if you look at where the red dots are on these plots, those are the objects that they detected. And they see a really different pattern when they make that distinction. And so that helps us understand how planets and how brown dwarfs are formed. So there's two different ideas about how those kinds of objects are formed. One is through, bottoms up, accreting little masses together to form a more massive planet or star. That's called core accretion. And then the other way is to start big. And to have that big disk structure, maybe around a big star, fragment down into a companion. And that's through gravitational instability. And so what they found is that actually there's likely to be different formation mechanisms for massive planets, massive exoplanets, and these brown dwarfs. And so, that's really great. That's a fundamental test of our understanding of how exoplanets formed. So there's a lot more exciting science that can happen with the upgraded Gemini Planet Imager. And you can see as we were unpacking Jwst and getting Jwst to really arrive at Gemini South, we were packing GPI up, sending it off on a truck, and it's now in the laboratories at Notre Dame. So looking a little further ahead, at the end of 2024, we're really excited to build this, to have a new instrument called Scorpio come online, and that's going to arrive at Gemini South. And I talked a little bit about imagers and spectrographs. Well, Scorpio is both. Scorpio does all the things in an amazingly efficient way. So it will cover a very wide wavelength range from the ultraviolet all the way to the infrared. It can get simultaneous imaging in that full wavelength range, or it can get a spectra in that full wavelength range. And so it's designed to be highly efficient. And it also has a special mode for if you really want data fast or you want to sample your data really quickly, it has a rapid acquisition and readout. So we imagine in the era of discovery, when there are new things being detected every night with the Reuben Observatory, people just want to know, what the heck is this? Gemini with Scorpio is going to be ready to very rapidly characterize a lot of the new things that are discovered with Reuben Observatory. So an example of what that might look like comes from this, LIGO detection in 2017. And so this was the first gravitational wave signal detection, which came from a neutron-neutron star merger, and the first one that had a visible counterpart, what we call an electromagnetic counterpart, where we could say, that's where it came from. And let's get the light and take a look at the light and see what that tells us. So Gemini played a critical role in the follow-up of this object, but we had to use two different instruments, an optical instrument called GMOS and an infrared instrument called Flamingos. So we had a 30-day campaign, multiple people put in proposals, and that data was really critical for helping interpret what kind of system that was. So we know it was a kilonova, this merger of two neutron-neutron stars, and we could see that evolve with time, and so help constrain some of the physics with kilonova. Another time-critical set of observations is the follow-up of these new interstellar visitors, which are just now being discovered. So I talked a little bit about Oumuamua, and again, by getting data over multiple days, we were able to constrain the shape of this and see that it had a really unusual shape, this long cigar-shaped asteroid. Another thing that Gemini helped solar visitor was the first extrasolar comet, which is 2I Borisov here. And you can see this great press release image where you can see the fuzzy comet, and it's moving through the sky. And so the stars, actually, when you line up on the comet, the stars look like streaks. So I'm getting close here to the end. I'll just say Gemini, as I said, is really well poised to answer a lot of what we think will be the fundamental questions coming in the next decade. And, you know, we've got all these great instruments on top of all the instruments we already have coming. And so stay tuned. I expect there'll be lots of new discoveries with Gemini playing a critical role.
Fantastic. Thank you so much for that really detailed and very informative presentation, Jen. I am excited to hear about all of the new instruments coming and the upgrades happening. Let's check back in with Rob really quickly before I do our science update and wrap up here. Rob, do we have any additional questions from our YouTube audience?
I don't see any additional questions in there right now, so you must have done a good job explaining things.
All right. Okay, so as you alluded to earlier, there is a new press release out, and it talks about, well, we have some new insights about Uranus, Neptune, and the differences in color. So I will share my screen really quickly. And this clip, Jen, it's a little over a minute long. And afterwards, we'd appreciate maybe your some insights on it.
Sure.
Excellent. Thank you. So many of you may have looked at Uranus and Neptune on your own through a telescope. And Uranus, a friend asked me yesterday, what's my favorite planet? And I said Uranus because of the color. And now here we see that the excess haze on Uranus, that buildup, makes it appear lighter color than Neptune. And we will drop the link in the comments later. But this conclusion comes from modeling, and maybe Jen can talk to us about that. It matches the observations of both planets. And that is a subtle difference in color, but it is a noticeable difference. And one of the other things that I love about this is that, of course, this is a collaboration, and that's how we came up with these with this new insight. And maybe Jen can speak a little bit more to those collaborations that we do that gives us such amazing insights. And let me stop my share. Yes, please, Jen. Thank you. Can you tell us a little bit about that? Gemini helping explain why Uranus and Neptune are different colors, and how we do that collaboration with Hubble Space Telescope, for example.
Yeah. So I think, you know, these are collaborations that are often led by our scientists, right? So, you know, they get a great idea and they're just interested in a particular science question. And so, you know, we have synergistic observing programs with Hubble and with Gemini, which is, you know, a great opportunity. And then, of course, there's also our archive where people can grab existing data from Hubble and grab existing data from Gemini and make that connection. So they often provide really complementary data sets, right? And so one of the things that Hubble does not have is a lot of spectrographs, right? They don't have the kind of capability to address this question of what's the atmosphere of Uranus and Neptune made up in detail. So that's one place where we can really work together, which is fantastic to see, and that this team doing that. I'll just say, you know, I also think that the connection between modeling and theory and data is also really critical, because it's not, if you just make a model and it's a great fit to Neptune, but it doesn't explain Uranus, then you know, you need to figure that, you know, they both exist. The physics should be roughly the same. Maybe the conditions are different. And so that's essentially what, you know, that comparison to a physical model to the data can really help you understand is this consistent? If I look at a different system, what does that tell me?
Perfect, perfect. Thank you so much. I love Uranus, and I haven't fully read. I've read this press release, but I'm going to delve into a little bit more because I literally was just talking to a friend about my favorite planet and pointing out that it's the color. So now I'll be able to have a better understanding of why there is that difference in color. And thank you for touching on the modeling, because modeling is used so often to help us refine what we're learning from our data. And so yeah, that was perfect that you touched on that. And I wanted to come back and revisit, and I know we're right at 3:00, but we're just about done. You mentioned the stellar stream, the press release that came out in January. And I would like to say we did host Kim Vinh, John Pastor, and Andre Nicolas Chenet on, they were discussing GRACES and the stellar stream. So we can also make sure we have a link to that in our video notes once we post the recording to go back to that. So thank you for mentioning that. And I'd like to say thank you, first of all, to Rob for making sure to convey to us all the comments and questions from the YouTube audience. Thank you so much. And our guest, our amazing special guest, Gemini's director, Dr. Jennifer Lotz. Jen, would you like to leave us with anything that you'd like to share with us?
I'm so pleased I got a chance to do this. I hope the people watching got a little bit inspired. And stay tuned. There's going to be a lot of really exciting science in the next couple of years.
Fantastic. All right. So one last question, actually, for both of you, as some of our regular watchers will know that Rob does amazing astrophotography, and we had an interesting new-ish meteor shower over the May 31st, the Tau Herculids from this very interesting comet that kind of broke up in the 90s, but I believe this was discovered in the 30s. Could either of you give us some insights on this newish meteor shower? And we'll drop our social media link because we did make a post about this. Rob, any insights?
Well, I was out observing it the other night, so I actually went out to observe it and was out for about an hour and a half or so around the peak time. It's forecast to be a very narrow peak, and there was not a meteor storm, so the meteor storm did not materialize. But I would say it was a very good meteor shower. It's like if you went out and saw there's maybe a meteor. I count about 60 meteors in 45 minutes, which is pretty darn good for a regular meteor. Now, it wasn't just me counting, there were other people there too, so if I didn't see one, someone else picked it up, so we had sort of a group collaboration thing going on. But still, it was better than one a minute, which is pretty good for a meteor shower. I got some pictures of meteors, I had a couple cameras going, and I'll put it in the chat here briefly, there was an A-pod today, not mine, someone who was on Kitt Peak, an astronomer on Kitt Peak from Stewart Observatory, who photographed the meteor shower and layered all the pictures together to make a composite of what he saw up there, which is really, really cool. So I just put that in the chat for everyone who can go there and see that picture. But I thought it was a good meteor shower, but not a storm. But it would be a good meteor shower on any other given year. I don't know if Jennifer has anything to add about it.
It was cloudy here in Hilo, so I was all set to go check it out, but I wasn't. So I'm glad. I'll go check out your pictures. So I'm glad it was not cloudy in Tucson.
Well, yes. I haven't taken all my pictures and put them together trying to do composite like he did on Kitt Peak, but his A-pod is pretty spectacular with the Bach and the Mayall 4-meter telescope in the background.
I just clicked on your link to the image from Kitt Peak. That is absolutely stunning. Absolutely stunning. Thank you so much for sharing this, Rob. With that, I'd like to say a final mahalo nui loa to our moderator, Robert Sparks, and to today's amazing special guest, Gemini's director, Dr. Jennifer Lotz. Coming up next month, we have our next live from NOIRLab. Rob, would you like to speak on that? Because I think that's Chile, right?
That's Chile, and I don't know what they're doing. They haven't told me yet. So.
All right, so it'll be a surprise for everyone. But of course, it will be an update from our NOIRLab facilities down in Chile. I'd like to say thank you to everyone for your comments and questions. We really appreciate your support. Thank you for watching us. And we'll make sure that any links to things that Jen talked about, the science update that I gave, and the link to the APOD is also in the video description once the recording is posted in a few days. Thank you so much, and we hope that you enjoyed this presentation.